Mic check. Good morning, everybody. Next to last week of class. So hopefully you're doing well and headed for a strong finish to the semester. Okay, we're in week 16. So the big thing for your class is that we have the project due this week. So hopefully you've been farming up procedures. So I'll just sort of point out to you what's going on in the schedule. Alright, so we're in week 16 here, so we'll talk about how do you translate high-level loops into assembly style. And again, just for your sort of longer-term experience in software, just kind of having a sense of what does a for loop actually mean when the processor has to execute it. The idea is that you might make better choices about writing loops and which loops to use if you understand how they translate onto the processor itself. As you might guess, it's going to be based on comparisons and jumps and labels, just like decisions. The main difference is that loops need an ability to jump backward because they need to jump back and then go back, repeat a sequence of instructions. Individual project 2 is due on Sunday for you guys. So when we meet again next week, you'll have 1 week's regular material left. We're going to do floating point numbers. Doubles is probably how many of you think of them. It's not connected to the project in any way. They're hard to do in assembly. So our last week will just give you some sense of how floating point numbers work on the processor, which is very useful information if you work in computers. But the content itself is not connected to the project, so there'll be a discussion, there will be a lab, there will be homework as normal, but we're sort of past the second project, so that's just one last bit of content for you to encounter. So who's here? Morning, Etsia, Captain Price, Glazer, Salinity, the Saddest Kitty. Good morning to everybody. Glad you're here for the last week of class. So we're going to do just like we did Canvas's. I'm not getting good network performance this morning. Just like we did last week, though, we'll look at sort of we'll look at some of the common loops, and then we'll pull up individual project 2, and we'll add a couple more features, and then hopefully I've left you in a good position to finish. Good morning, Etsia. So check it out, week 16 of 17. I don't know about you guys, but this is the first time that I have ever done online start to finish in a semester, and I find it more challenging, more difficult to manage my time and myself and my state of mind over time online. I don't get to see anybody, I don't get to talk to anybody, so morning, Tyler. So I'm glad you're all still here and still going at the work. Okay, our goals. So we're going to do loops. We're going to use comparisons. We will use conditional and unconditional jumps and statement labels to write loops in assembly language. And then, same as we did last week, we'll do a lab where we translate. We get a lab that's already completed code, and we'll translate the loops that are in it into low-level code. So a little bit more reading, but more or less the same deal, right? So you know how that part works. Homework as usual. So the lab I'll come back to. And then second to last discussion. So I don't know why, I'd like to have your group sort of give yourselves a better base of knowledge about what we do in software. So there's actually a Wikipedia article about the for loop, so we'll just try to get a discussion going about for loops and where they come from and how they've been used, whatever it is that you can find about the for loop. I just think it's kind of interesting that even the for loop has a history, and even the for loop probably has debates in our line of work around its implementation and its use. Okay, so there's those things. I'm gonna get the lab queued up, get the code for the lab queued up so I can flick back over here in just a second. The first thing I'm gonna do though is go into a virtual machine and just talk about the common loop styles and what do those look like in assembly language. So this I'm just queuing up for later. Okay. So let me get logged in and then we will toy around with them a little bit. So one thing is this is, oh, it's already there. One thing to remember is that you have to, before you write a jump instruction, make sure you are aware of if you have just run a comparison on signed or unsigned integers. If you have just run a comparison on signed integers, let me write this down and then I'll ask chat. So yes, so Captain Price asks, is converting loops into low-level code easier than if-then statements? And I think it is. It's easy to get confused, but as long as you're working in sort of a confined area of code, I actually think that in some ways, well, I know for sure that translating loops are easier for me than decisions because you don't get the rat's nest of branches, you just have the one loop. Okay, so comparisons of signed integers. Do we do above, below terminology or greater or less terminology when we're comparing signed integers like int8 and HLA, anyway, int8, int16, int32? Is that above, below, or... Yeah, no doubt, Captain Price. A lot of people had logic issues, so we'll talk about that, and it is just difficult to get it working right. Okay, so Captain Price is correct. It's greater or less when they are signed, so you need to be very, very careful about that. If you fire off a comparison on an int8, an int16, or an int32, the thing to think about is, could my value at the moment be negative? If my value can be negative, I need to be very careful and make sure that I'm using greater or less semantics, right? So it is greater less. Which is all of the jump instructions that have the greater or less terminology in it, right? So jump greater, jump less, jump greater than equal to, jump less than or equal to, jump not greater than, jump not less than. There's a whole bunch. Notice, by the way, well, let's just start with that. So comparisons of unsigned. Use what semantics? Greater, less, or above, below? It's a good question, Captain Price. Give me a second on this one and I'll answer that. Above, below. Above, below. Very easy to miss. Jump above, jump below, jump above or equal to, jump below or equal to, jump not below, jump not above, etc., etc., etc. What? I'm trying to make these. The things that are always the same, equal, not equal, those are the same no matter signed or unsigned. Okay, so Captain Price had a good question about, well, what's more annoying, compiler errors or logic errors? Logic errors are far more annoying. It's actually compiler errors. You actually look forward to compiler errors because at least the compiler found the error and is helping you fix it. But a logic error, there's there's nothing that's going to help you very much find a logic error. So the logic errors are way tougher to deal with than compiler errors. I love aggressive compilers that emit lots of errors because that is less time I have to spend hunting down the problem than just fixing it. Because the compiler tells me exactly what I did wrong, exactly where I did it once you've learned how to read compiler errors. So that's a good question, and I personally think that runtime or logic errors are way worse to deal with. And my bet would be that all of you will get to the point, if you're not there already, where the runtime or logic errors are just way worse to deal with. Unknown end token, that means that something got mismatched somewhere. Or you use the keyword end. So sometimes, Captain Price, if you get an error that's sort of a mystery error in HLA particularly, about some word that you use, that's often because it's a reserved word in the language and you need to change your identifier, your labeling to not collide with the language's reserved words. So that's often what that could be. But also, if you get an unknown end token, it may be a mismatch. So yeah, these are hairy, and I have a recommendation about that when you start working on the... let me just save these as notes. December 7. I have a recommendation for the project when we start talking about that. Okay, so let's do some loops just to see how those translate. They're not hard, but they are a pain. And as Captain Price is pointing out, it is super easy to make mistakes and introduce logic errors, and those are very difficult to find. But just nature of the beast, they are difficult to find. Okay, so let's do some loops. So that'll be my low-level version. This will be my high-level version. That one did not go in the right place by default, so be careful about that. Okay, so let's do a forever loop and then translate that. Captain Price brought that one up. So in HLA we have the forever loop, and then we usually will have something like I'll say R to repeat. Get a character off of it, and then we'll say, I'm going to cheat. This is a HLA standard library procedure, so when I get C, I'm going to get the input in AL, and I'll just immediately uppercase that so that I'm case insensitive. Yeah, so that just, as Captain Price is pointing out, that just, that way I can press a little R and it has the same meaning, or a big R, if I accidentally do that, it has the same meaning. So remember, forever loops really are dependent on somehow breaking out. Now technically, this break if is an if, so we should do that in low level too. Okay, so there's the forever loop. Now let's translate that. Now I like to put my labels, remember, on the far left, but you can put your labels wherever. And I also like to uppercase them and use underscores because it makes them pop when I'm looking at code. Now typically I just know from experience that I'm going to need a starting point and an ending point to work with for my loops. I need somewhere to jump back to, and I need somewhere possibly to jump forward. But let's see how we can. So just sort of start with that idea, but you can then actually eliminate a piece. Yeah, so let's do the standard output, press R to repeat. So now we're going to compare, and we can just do the same compare, so it's a good question. Captain Price. So in this case, we're not doing above, below, we're just looking for equal, not equal. So you can actually do the comparison of the character in the register that's been stored as input and what you're looking for, and then you can do comparisons of equal, not equal. So if those are equal, if their input is a big R, then we'll start back, we'll jump back to the start of the loop. Pretty cool. Actually, if it's an R, then I do want to repeat. So you could say jump not equal to the end, but then you'd still have to somehow get back to the start. So you can do this, if that's and there's nothing wrong with what I've written here, so if this is the way you can work out the logic, then totally do this. So if they're not equal, I can jump to the end, and if I get to this unconditional jump, well, it means that this conditional jump didn't happen, and the loop will repeat. But it turns out that I can sort of get rid of the middleman here and just say, if it's not an R, if it is an R, I'll just jump to start, and in that case, I can actually get rid of the end label. Because if I don't do the jump on equal, then so you don't even need the end label. But there's a reason why you might consider using the end label. It's because in this code, it can be difficult to see where the loop section sort of begins and ends. So sometimes I will, and often in fact I would actually include an end label even if I'm not going to use it, just so I can sort of easily see where my loop begins and ends. I happen to like this style because now I can kind of pretty easily see where the looping section starts and ends. Even though I don't actually use this label or need it, it still helps me better understand the code. Remember that a label that you don't jump to doesn't hurt anybody. You can put labels and not jump to them. It's fine. So yeah, we can't really. I've actually never tried recursion in the assembly style. Which I don't even think you can, basically. I don't know how you would do that. Anyway, so there's a forever loop. Here's the break if, the translation of the break if. And the end forever loop is not doing anything except for making it easy for me when I'm reading the code to understand where the section that's designed to be looping ends. I don't jump to it, I don't use it, it doesn't affect anything, it's just there as a marker. Literally in this case just a dumb label that just sits there so that I can read my code easier. So there's a forever loop. And then I will comment those out. Seems like recursive, like redefined. I can see that. So yeah, Captain Price and Gersavok both have that. It sort of makes your mind think of recursion because you're coming back into the same sequence of code. So technically not recursion, but recursion at the assembly level doesn't really exist. It's a trick of high level languages that sort of causes a function call stack that kind of works like a loop. Anyway, this is different, but it's not wrong to sort of think of recursion, because recursion really is just repeating a process if you think about it. And that's what we're doing with our loops, is we are really just causing a process in code to repeat itself. Okay, so there's, but yeah, I don't think it's wrong to sort of have that enter your head, because why are these? Oh, I can see why they're different. Let me push this down just so that they kind of match. No, I'm not going to do that. It looks weird. Okay, so now let's do a for loop, and you can imagine the others, but we'll probably do a for loop, and then we'll do a repeat until loop, and just to get a feel for how those things work. So for move 0 to CL, CL less than 8, inc CL. Let's just print a counter value with a for loop. And then we'll see how that unravels in assembly style. And then we'll go from there to a repeat until loop. All right, so here's a for loop in the high level style. Let's do a for loop in the low level style. Start for, end for. So I'm just sort of giving myself some guideposts. So if we are mirroring exactly how a for loop works, you sort of have to know how for loops work. The move 0 to CL, that actually doesn't ever repeat itself, even though it's in the for loop syntax. It actually doesn't get repeated, so that would be something when you're translating that happens before you start a repetition, right? Because this never repeats itself. So even though the for loop makes it look like it's somehow part of the whole scheme, it's actually not technically part of the whole scheme. Now you also have to understand that in a for loop, the logic, the controlling logic, is actually happens first. So you actually have to compare CL with 8. Yep. So compare CL and 8, and then what happens, so you have to understand then, yeah, but you have the, okay, there you go. So Captain Price is already on it. The whole point of this comparison is to see when we need to stop doing this. So we want CL to be below, so this counter is 0 and up, so we can do unsigned comparisons on it. So this will be 0 and up, it'll be an unsigned comparison. So if it's below, we want the repetitions to happen when it's not below, so you can do not below. So if CL is not below, and we're doing below because this is unsigned, 0 and up, if CL is not below 8, then let's get out of here. Now I prefer, just because it makes more sense to my mind, to say if it's above or equal to. So if CL is above or equal to 8, then I go to N4, but you can also jump not below. Totally up to you. They're the same thing. All right, so this one's more fun, so get ready. Yeah, Captain Price, that's the one that I like too. So, but again, you can do not below, and that works just as well. Okay, here we go. So, if we don't do the jump, then we want to continue the loop. So we want to print this thing, and then the whole trick is what goes on line 13. Nice one, Captain Price. So jump, start for. We need to get back and repeat the whole thing. And notice the move won't happen because the start for is just beneath it. Oh, we forgot something. Thank you. Captain Price got it. Yep. Thank you. Good on Captain Price. Print, increment. So you could use the INC instruction or add one and then jump back to the start and repeat the whole process. So there's a for loop. It's more complicated than a forever loop is because of the nature of the for loop. I'm going to translate this for loop into a while loop. So there's a while loop. Yes, so Captain Price has a question here about jump greater than or equal to. That would work. So the thing to be careful of is if the number could be negative and you use above, below, it won't function properly. If the value is guaranteed to be positive, then it turns out that above or greater are all okay. But I would get in the habit of just, I mean, you only have one more week to worry about this in life probably, but try to get yourself in the habit of recognizing if these are signed or unsigned, and get in the habit of above, below for unsigned and greater, less for signed. Yes, so Captain Price has noticed the while loop is the same, which is a little insight to gain, is that while loops and for loops really aren't different. For loops are just a convenience that sort of build into themselves a lot of the things that we often use inside of loops, but they're really just more complicated while loop setups is all they are. So it's the same translation unless you wanted to change the labels. Same translation, exact same thing. So yeah, for loops and while loops are pretty much the same loop. For loops just, it's meant to be a convenience for programmers that it sort of builds into itself. The counting components, like the counter variable and the counter logic and the counter increment are all built into the for loop, but they're really just fancy while loops is all they are. And they translate exactly the same. It's just, I think, kind of cool to see. Okay, so now let's do a repeat until loop, which is a do while loop in many languages. Take this guy out. So one more loop, and then we'll get back into some project stuff. Now, I think I said it last week, but I happen to like this. It's an interesting sort of programmer brain teaser to translate high level to low level, even though you'd rarely do it in the real world. I like the process. I like kind of seeing what are these loops actually sort of encapsulating in terms of how processors work. So I think that's kind of cool. So let's do a repeat until. We'll do it this way. So I'm going to do signed just to force the issue. Okay, so there's a little repeat until loop. The main difference with the repeat until loop and the others is that they're guaranteed to execute once. You probably already know that. So let's translate this thing. Start, repeat, and repeat. And again, I usually just fire up 2 sets of labels around my loops. I like the way it looks in code. I think it's easy to find and easy to kind of read if you have your loops marked off like this. So let's grab this stuff. Okay, so now we're not getting any help, right? So we need to compare AL with 99. And then this isn't until AL is 99. So on 99, break. So what's the jump instruction I use and which label do I go to? There's 2 ways to do this. So I was tricky here, tricky on purpose. So remember, I'm doing signed. All right, jump not equal. Nice. So where do we want to jump to if they're not equal? So you're on it. If they're not equal, then we want to repeat. So the start, there you go. Good one, Tyler. So start, repeat. So as long as they have not entered 99, we're just going to restart. So notice here, then this was clever, Gersavok, because the way you wrote it, we don't actually need the end marker. The loop actually doesn't need that to do its work. If it doesn't do this jump, then the loop is over. I like having the label there because it's easy to see where the loop starts and ends, but we don't actually need it. All right, so let's do one more challenge for ourselves. If they're equal, I want to end. And that's okay to do, but I need to do something. If I were to jump to the end when they are equal, then I need to add something to make the loop actually continue to work. So what do I need to do on line 16? If I want the loop to still function. Okay, what do I, so I do need to do something with start repeat. How do I get myself to start repeat if I didn't do this jump? Nice one, Tyler. So I can unconditionally jump from the bottom of the loop and cause the whole process to repeat. So it's perfectly fine to write a loop like this, where I actually am looking for what ends the loop, but then I need to be careful that I unconditionally jump back to reset and go back through the loop again. So that's 2 ways you can do it. This one has 1 extra jump in it, and it actually needs the end label to work. So those are both valid ways of going about that translation. Up to you. It often is a matter of, for me anyway, it's often a matter of which, like right after the comparison, what makes the most sense to me to check for. So if I'm writing it to be exactly like this loop, then I am going to write jump equal, and then I need to figure out, well, what am I supposed to do on jump equal? And then I have to think what happens if I don't. No. So Garsavaya, it's a good question. So do we need any kind of incrementing? And with this loop that we wrote, we're not. We're just repeating a little process where we ask them for input, and they give input, and they have to type 99 to quit. Okay, so this was a good exercise, at least for me it was, hopefully it was for you too, to kind of get a look at the different ways you can go about implementing a loop in assembly. All of the ways that we looked at are completely valid. It's perfectly fine if you get extra jumps, if you end up doing extra compares that you didn't need. The whole point is to make sure that the flow of the logic works as you intend for it to work. So that's your primary goal, is to make it work. Making it work beautifully is a secondary goal. Now, if you go into like control systems for rockets or automobiles or something, you're probably going to have to make it work perfect the first time because they have very, very, very strict standards. But if you're writing a game or a consumer product like a word processor, you can probably just get it working decently and then get it working beautifully later. So some industries demand working beautifully as a primary goal, and other industries are a little bit more flexible about that. So if you do web development, for example, up to a point of very large scales like Twitter or Facebook, it doesn't really matter as long as it works. Okay, so there's some examples. I'm going to bring up the lab and let's have a look-see at what the lab looks like. Can I close this? If I do that, okay, so let me go get the lab code and paste it in here, and let's just see if there's any scary stuff going on, other than the scary-ish translation. So let's see how many are in here. Probably 7 if I had to guess. Okay, so lab 16. Here's a forever loop. So this one's a little bit more of a pain in the rear, but let's do this one together. The forever loop on the get int 8. By the way, this is a freebie. If we do this, then you totally have it for the second project, and it's all translated and all the goodies are attached. So that's a good question, Gersavok. So what's the jump words for Boolean? So you actually have jump true and jump false labels. So you could have you can also, so you can do, well, you can actually just do, yeah, that would probably be okay. There is a jump true and a jump false. You can also still do equal in those cases, but there are jump true and jump false jump labels. So hopefully that makes sense. So JT, jump if true, JF, jump if false. It doesn't work for me in the vert, for example. So Tyler has a question. If the syntax highlighting isn't working, you can, if you go down here to where it says plain text, like right now mine says plain text. If it's not highlighting, there's 2 reasons that can happen. One is that it just never switched to HLA, so you can click on plain text down here, and then you can scroll down this list of languages until you see HLA, which should be in there. Double click that, and then it'll start highlighting. The other thing to check for is that you saved it with a .hla extension. So if you didn't save the file with .hla at the end, that can also not trigger the syntax highlighting. So it should be one of those things. Oh, good one. Good one, Glazer. Yeah, I forgot about that, actually. So what Glazer's saying is you can click on this list down here, and you can type HLA, and I don't know why, and then just press enter, right? And then force it. So that's what you can do, is just force the issue by selecting the language explicitly. Good question, though. Gerstbach, hopefully I got the answer to that question. So we have jump true, JT, and jump false, JF. But you can also compare, you can also do a comparison, and then you can check for equal, not equal is basically the same thing. But you can do a jump if true or a jump if false kind of thing on it. Okay, so let's do get innate. Yeah, and then let's see if we can add a little bit to the second project. So this one looks a little bit scary because it's got the forever in for. So let's get rid of the opening label. Okay, Tyler, that's weird. If you're using the class's virtual machine, because I built it to have that syntax highlighting in it. So if you're using the virtual machine you downloaded for the class, it should be in there. Now, if you're using a different virtual machine, it won't be in there because I had to handcraft that syntax highlighting for our class. So I don't know. That's a little bit funny if you're using the text editor. But yeah, we can look at your screenshot. Okay, start forever. End forever. I got my labels in there. Now we just need to figure out how to get to them. So this is all the comparisons. And the problem is right here. So the problem is this break won't work with labels, but all I really need to do on this break is get to the end. So, and then the hard part. So the break was actually causing the loop to get to its end. So that part's easy. The hard part is getting back to the start. So that's actually the hard part here, is getting back to the start. So this whole try and try, you got to remember how it works. It prints a prompt. It tries to get an input. It then looks at the value that was entered. If it's less than the minimum, then they get the bad section. But it has to compare again. If it's greater than the maximum, they get the bad section. If it didn't jump to either of the bads, then they're good to go and they can leave. But they might have gotten a bad input, and they might have put something that wasn't even an integer. So the trick is you have to understand that you have to let this whole try and try play out before you force the process to repeat itself. So I'll pop those out so that they're a little bit easier to see. Oh, Glazer's got it. That one's for Tyler, by the way. Hopefully, Tyler, you saw that in chat. If you press, let me see what F11 does. Oh, yeah. So try that. If you press F11, you lose all of those goodies. But if you press F11 again, you get the goodies back. So maybe that's it. Good call, Glazer. Okay, so that's a hard one. Now, with that, by the way, you now have get int 8, get int 16, and get int 32, which hopefully you can manage implementing for the project, which gives you some bonus points, kind of, because you get some of the low-level translation. So this one is one of the more difficult ones because of the try and tries to figure out when to reset. So the reset is at the end of the try and try, where you let the potential error messages pop out before you jump to start forever. But remember, in the meantime, you may have jumped to end forever because you got a good input off of them. Okay. So that's number one. So number two, I guess I'm doing on time. Let's do number two. Okay, so this brings up an issue because you can't do this. I believe you're going to get a compiler error if you do this because you've already used this label, even though it's in a different procedure. It's in a different, it's the same label. So I highly recommend that. I usually do it like this. I just kind of attach it to the procedure that I'm in. So this is my forever forget int 8. Now this is going to cause all kinds of problems, but I need to change all the labels in here to make sure that they are all get int 8 labels. And you might even do these, well, that one's probably okay. Anyway, so this is my style. I like to have the labels be highly readable so that I know if I see a label inside of with get int 8 on it, I know I'm still in the get int 8 procedure. That's something to consider. You could number them instead. You could do start forever 1, end forever 1. So you can make these ones and then just number each. But I personally think that the little bit of extra work to actually make it more readable is worth the trouble. So this start forever is in main. And the main part just tells me that's where this label is rooted, is inside of main. So there's the start forever main. Let's go get the end forever main. It's right here. Uh-oh, there's two of them. What's the second one about? Well, I'm what is that the N4 for main? Yep, it's 2 sections, so you got to be careful here. Start forever main. So in this case, main has 2 labels. This is a pain, isn't it? This is the first one. Or you could say this is the menu section for main. Here's the N4 for that. So this is hard. Start, this is end, forever, main, menu section. And then when I do this one, I can call this like the counter section. Something like that. Just so you know, it's worth the trouble, in my opinion, to take the extra time to type the extra stuff so that it's easier to understand what's happening. Let's finish this one. So we need to know how to get back to the start. We need to know how to get off to the end. So let's see if there's a break or something in here. Here's a break. So we can just jump end, forever, main, menu. That gets us out. And then typically you just go right to the very bottom before the N4 and you jump back to the start. Now that, nope. Now that loop is translated. So these are harder. I'm going to switch our view. Tyler, by the way, if you could screenshot into Piazza or something, and then I can flick over there at the end and have a quick look, maybe. Okay, so these loops are harder. I will remind you, and I'm going to remind you this about the project. No one thinks worse of you if you choose to not do a lab or you choose not to do all of a lab. I mean, I think you're maximizing the value you can get for yourself if you do the exercise of these translations. But you also have your 2 lowest labs are dropped. So if you've been doing everything and been doing great the whole semester and you just hate this, take one of your drops. It's not going to hurt anybody and no one's going to think less of you. So just pointing that out if you decide that you feel overwhelmed by this. Of course, reminder also that the first thing you should do if you're going to do this lab is download it, compile it, run it to see what it does, and then translate it, compile it, run it to see if it still does what it used to do. Okay, so let me switch the view and bring up the second project before I do any more coding work. Okay, the second project, I just want to point out to you right here. So 100 of the 500 points are translating the high-level stuff into the low-level stuff. People historically in this class, people who have just sort of knocked everything out of the park all semester long, realize that they can afford to give away those last 100 points, and they just don't do that part. So what I strongly recommend is that you implement the whole second project with high-level loops and decisions. You don't have to, but I recommend it. And then you judge for yourself how much you want the experience and how much you want those 100 points for doing those translations of the high-level loops and decisions to low-level loops and decisions. No one will think less of you. It's not uncommon that people have sort of min-maxed the class this way historically and just decided that that was more misery than they cared to undertake. So I just point that out to you, that a lot of you are in a position where that's not going to do any harm to your semester grade. But do the math and see if you can afford the points, and you can make that decision. But it's one reason why I recommend at least that you do it in a high level, so you have the option at the end of submitting the high level one that works before you make a mess for yourself doing the low level translations. Okay, so I'll bring up Piazza, and probably haven't got there yet, but okay, so I'll have that ready. Anyway, so that's about the second project. Now I'm going to bring up, let me switch the view again. How are we on time? We're doing good on time today. I'm going to switch the view back, and I'm going to bring up what I have going for my second project, and at least suggest one way of solving one more part that I think is slightly more challenging. I forgot what I'm doing. Oh yeah, second project. Okay. Called sheet. Okay, so I think I already, let me spread this out some. I think I've already recommended some things. Did I forget to save it last time? I don't remember. Okay, so where's the print? Oh yeah, so we did the what format do I print it in logic last time, and that started with a variable, so that we can keep track of what format we're supposed to be using at any given moment, because we need that to do logic in the program. So we're going to add one, which is m operations 8 equals 1. So we're going to do a similar thing here. Something like that. We're going to add another variable so that we can keep track of a code that tells us what operation we're supposed to be applying at any given moment. So if you look at the screen captures for project 2, which I got to switch my view back. Oh, I didn't do screen captures. I did runs, didn't I? You have to run it. Okay, well, I'll just run it real quick, and then we'll show you. But let me show you what I'm talking about. Okay, so yeah, you can't see that yet, so let me add it. Okay, so here's the running program from the sample directory. I want to show you which part we're working on. So we've already actually worked on this first part. How many cells do you want? I'll say 5. Select the desired data type. I'll say 2. It does the allocation. It adds an extra cell, remember, because we're doing a calculation into one of them. So here's the displaying int16 values in decimal. I actually added the little extra bit. You're working with int16s. But there's that thing that we did last time. You are viewing decimal, and it will switch to binary or hex. Right, so if I change the presentation to be binary, now it says you are viewing in binary, and it pulls up the proper presentation. Okay, so let me switch back so we can make sense of this better. Change presentation back to decimal. Okay, so now we're in decimal. So what we're working on is how does it know to print the word sum, and how does it know when and how to calculate the sum? Well, how to calculate it is a procedure which we will write. The label is because of the code that I just created. So that M operation, that's the code that tells me not only what label to print, but also that it needs to run the summing operation. So the way this works is every time we edit a cell, cell number 1, I'll enter a new value, -10. So every time you edit a cell, it actually reruns the calculation. So you did an edit, and then it automatically reran the sum. So it used M operation again after that edit to know that, oh, I need to also run the sum procedure again. So that's how that works. So that's what we're working on here together is how do we implement that? Okay, so I need a code because I need to figure out, as the program's running, what label to print and what operation to run when they edit their data. So let's go down to print. So there's the current format. I also could have done something fancy with the type and said current format for your int16 array. Okay, down here where it says calc, let's improve that, shall we? So we can use, now we're going to need it. We're going to need to know the operation code, which I'm just going to lazily call O. So O is going to tell me what operation code. So right here, instead of calc, I'm going to use that as a model, but I'm going to say if O equals 1, that's sum. Else if O equals 2, then min, doesn't really, these are just the codes that I happen to pick right on the spur of the moment. O equals 3, then max, else. I only have those 4 operations, so that's the only other possibility that's legitimate. So now I can get rid of this calc thing. Okay, so now I've just used my operation, which the procedure thinks of as the parameter O. F is the format, T is the type, int8, int16, int32. S is the size of my array, and A is the array address. Okay, so there's how I used operation just for printing purposes, which will print out the appropriate label. Now the other trick is, when I call print, right here, I need to pass M operation so that the printing knows the operation. The other thing is, print. So let me start showing you. My setup here. So here's my running program. So we did the setup. How many cells do you want? What's the data type you want? We compute the proper number of bytes to allocate and allocate them, zeroed out. Then we store so we have the M size, we have the M type, we have all the settings worked out. We have the size, we have the type, we have the array address. We defaulted the format to decimal and the operation to sum. Those are defaults, but the menu needs to allow changing those things. So now we're in the running program where it prints the current state of the spreadsheet, and then it prints a menu asking them, okay, what do you want to do next? Do you want to edit something? Edit, cell, I can't remember what the options were. Edit a cell, change operation, change display, format, etc. Then we have, if they chose to edit, call edit and do that work. Else if they want to change the operation, then do that. Else if they want to change the display, then do that. These are a bunch of submenus, so it's easier if you put them in procedures. And then at the end of the entire thing, it'll always just say, press enter to continue, which I find super useful. Now after that, before we actually do a repeat, just get in the habit of rerunning the operation. So if M operation equals 1, then compute sum. And then we're going to have to pass the array, the size of it, and the type of it to do that. So I'm just using my coding system. Code 1 is sum, code 2 is min. Code 3 is max. And there's only one other possibility, which is compute the average. So whatever they happen to choose from the menu, if it was edit, then we reapply the operation. If they happen to change the operation, then we recompute. So if they do anything, in fact, no matter what they choose, when they select from the menu and you do what they selected, we reapply the operation just in case they did something that caused a change. Yeah, so Tyler's put out a good, I'll steal it, Tyler, and I'll put it in there since you did the typing work for us. So thank you, Tyler. Here's the menu. So, and then these are going to lead to submenus, and that can be easier to manage if you make yourself some procedures. Remember that you do have some global variables, so you can take advantage of that fact and alter the globals. So, thank you, Tyler. That's the menu. So you print out the data, and then you print out a menu, and then you get a choice Mainly do a submenu there. Okay, so I wanted you to see how M operation. I'm going to do one of these. I'll do, well, you can pick. You have min from an earlier lab, so technically you're not seeing anything new if you ask me to do that, but per your choice, if you want to sit through it for another few minutes, I will do sum or average. Unless you don't want to see it, and then I won't do the spoiler. But if you don't mind the spoiler, then you can weigh in and chat if you want me to do sum or average. One of those is the better choice, by the way, because it gives you something. Okay, so Tyler made the smart choice, which is average, which requires computing the sum, which means that you would have that somewhere in there. Okay, so let's look at what compute average would look like. I will put it in here. Compute average. So we're going to have the array address first. We're going to have the size of it, which I'm pretty sure is an uns32, although why I put two spaces there, I don't know. And then we have the type, which I think is also an, how do those extra spaces keep going in there? Is the type also an uns32? So the address is a D word, the size is un32, the type is uns32. Okay, so that's the three arguments that I need to compute the average. Begin, compute average, end, compute average. Let's be good citizens of the program and preserve the registers, and then we can just go nuts on them, right? So whatever registers I need, that's what I'm using. Okay, so one thing to note about the average here, these are integers, so you're only going to get the quotient, you're not going to get the remainder. Just note that that's by design. You're going to lose the remainder because we're working with integers. Okay, so to compute the average is a matter of computing the sum, dividing the sum by the total number of values, and then you have the average, right? So here we go. I will use EBX. So I'm going to sum into EBX. Now the reason why I'm using these 32-bit registers is because I'm going to use ECX as an index into my array, and indexes have to be 32 bits. S, that's the size. That's too many. No, that's fine. Yeah, that's perfect. So here's the pain part, because we're going to have to use the type to figure out how much data to take, right? So we're just going to do we're going to accumulate. Let's use A here. What the heck? So let's accumulate the sum into A. So 2 EAX. Ooh. These are 8 bits. So we're going to zero out all of it, but depending on the data type, we may only use right? So we're only going to use the 8-bit portion of this. This, by the way, can trigger overflows, so let's see if we can figure out how to deal with that. So we're going to add If in doubt, typecast. If in doubt, so we need the base address. So here we're going to need more stuff. So we need to move the address. I'm going to use B. You're going to use a bunch of registers. You just have to remember which is which. So base plus an offset, which is what my loop is doing, producing the offsets, times the scale, and add that to AL, which would be my running total. The only difference on the type 2, which is int16 code, is I'm going to do int16, and I'm going to accumulate onto AX because I'm doing 16-bit math, and then the last one, those are int32s. Oh, I forgot the scale. 2 bytes apiece, 4 bytes apiece, and then we're going to use all of EAX. Okay, so when we are done, so we have two things. One of them is kind of magic and aren't we happy? And the other one is because we did it on purpose. So at the end of the loop, AL, if it were int8s, AX or EAX are the sum of all of our values, not including that extra cell that we made for the calculation. And here's the magic part, ECX is now sitting on our extra cell. So remember, the size is actually only counting the regular cells, which means that whenever we write one of these loops, we sort of magically get the index of the extra cell when the loop breaks out. So we also have ECX sitting on the extra cell, which is just fantastic. Okay, so now we got to do a little bit of trickery. So we need to move the size into EBX. So this is going to feel pretty weird at first, but we're kind of purposely mixing signed and unsigned. The size is unsigned, but we're about to do signed division, and it will just work. And if you sort of put your mind to it for a while, you'll realize that it's safe to do this. It's safe to treat the size as signed as long as the size is not an illegal value for assigned. So for example, our size will never be more than 10, and that works just fine for int8, int16, or int32. 10 is the same in binary, signed or unsigned, in all those, all the different sizes we have. So this is going to be my denominator. This we haven't done much of, but we have to, is that the one we're sign extending? We do have to, no. We have to sign extend A, so we need to convert double word to quad word. Good thing you asked about this one. This one's a hard one. So because these are signed, I'll leave that note there. So this is the little bit of trickery we have to do to populate for the division we're about to do. So I'm glad you asked this one, because man, this is the hardest one. If we were doing unsigned, we would have simply moved 0 into EDX to ready that combo. But because they're signed, we actually have to use this. This stands for convert double to quad. But what it does is it takes EAX and it takes the 2 to the 31st bit and it copies it across into EDX. So if EAX is negative, that's going to be a 1 in 2 to the 31st, and it will copy 1s all the way across EDX. If EAX is positive, then that 2 to the 31st bit would be 0, and it'll copy 0s all the way across EDX. So this magical instruction either makes EDX all 1s if we have a negative numerator, or it makes it all 0s if it's a positive numerator. And by magic, that makes the math work out. So we don't know if we need 0s or 1s, so we just have this instruction from x86 do it for us. So EDX in the end will be all 1s if EAX is negative, or all 0s if EAX is positive, and then the idiv works. idiv, because EAX was the sum of signed numbers, which could be a negative number. Remember, EDX has now been readied for this by the processor, by this instruction. So when I get to the end, what I will get is EAX is the quotient, EDX is the, what am I looking for? The remainder. And then I have to go back to my types, and I have to put the quotient back where it belongs. Fortunately, I only have the 3 data types, so I'm going to move AL for these little ones somewhere. I'm going to move AX for the slightly bigger ones somewhere, and then finally I will move EAX somewhere. The last bit is the somewhere, which I need to get the base address back because I overwrote EBX. Yeah, there's not really any getting around that, is there? I need the base address back because I overwrote B with the size for this division. So I need to put the base address back. C was never touched, so it still is the index of the extra cell. So typecast if in doubt. So my newly restored base plus ECX, which the loop magically left where I need it to be. And then the scale is 1 byte per. This type 2 is int 16 x plus, and then 2 bytes per, and then finally 2 plus the magical plus 4 bytes per. So when this procedure is done, it has in it, I computed the sum, then I computed the average, just the quotient part of the average, and then I put the average back into the array in that extra cell based on the data type. So there's compute average. This, by the way, is compute sum if you were to take out the division. It's compute sum. So one thing I want to show you, I believe that it says you should detect overflows. So you can do that. Boolean. You can detect overflows if you want as well, and then print it. So let's look at how do we do this with the overflows. So the way we do that is down here when we do any kind of math that could cause an overflow, so these adds could cause overflow, we just check. By the way, you need to do this before you ever start. before you ever start a new operation, assume that the overflow won't happen this time. Unfortunately, you have to do this immediately after all the adds. So now every time we do an add, we can actually detect overflow. So if at any point in this loop overflow happens, we have a variable that detects it, and then we can use that stuff. And we'll just use it as the global that it is in print. Right here. Do these print with an end line on the end? They don't. So you can also, after here, you can say you can actually add to your output that an overflow happened, which should only happen for averaging and sum, but you can still kind of do that. So what I would recommend, it's probably getting some information overload on you now. What I would recommend is for every compute, do move overflow to false before you do the compute, in every one. And only sum and average do any adding that can cause overflow. So those are the only ones that you have to worry about it. You have a compute min, so that should be easy to convert to compute max. And compute average is the whole same operation, except for you don't have to do the division at the end, because you just need the sum. Okay, so that's a lot. Probably you've had enough. I'm going to go look at Tyler's screenshot and see if we can figure out what the issue is. So I hope that helps. This is due on Sunday, so if you need, don't forget that you can meet with me on, what's it called? The Zoom thing. Confer Zoom. So if you need to see me, please ask for a Confer Zoom, even if it's outside of the normal schedule. You can send me a... so yeah, if you need to do Confer Zoom over the project or anything else, if you can fit it in the schedule, that's great. But if you are already past where I have scheduled times, then please send me an inbox message and request a meeting time. Give me some options. And we'll schedule a Zoom time to work with you on your second project. But don't forget Piazza if you need help, if you have ideas, if you figured out something that you can share with everybody. So that's sort of the end of today's class. Tyler, if you want to stick around, I'm just going to do it here at the end of the video. So I'm going to switch over to Firefox and go look at Tyler's screenshot and see if we can figure out what's the issue. And hopefully we just quickly figure it out. But anyway, so for everybody else, if you want to stick around, you're welcome to, but I'm doing this specific syntax highlighting problem. And otherwise, I will see you next what is today? Monday. So I hope you do great on the project. Please let me know if you need help. Piazza, Canvas Inbox, Confer Zoom meeting. And otherwise, I'll see you next Monday. So switching gears to look at the syntax highlighting issue. This is a different editor, Tyler. So the issue is the editor. So do this. So you're not using the text editor on the desktop. You're using, you probably double clicked it and it opened it in the wrong text editor. So what you need to do is you need to double click on the text editor on the desktop. You'll notice the controls are all different. So if you go into the folder and double click on one, or you right click and say open with text editor. Oh no, that worked. You double clicked it. Okay, so if you go into that folder and you double click something, it opens it in a different editor. And see, the controls are all different. And I don't have syntax highlighting for this editor. So you can right click it, open with text editor. It's the one with the red pencil icon. And then notice the controls are the same as what we're seeing, and it has the highlighting options back. Or you can double click the one on the desktop first and then open it from there. So anyway, I think that should get you good to go. It's just that you double clicked it and it opened it in a different text editor that I didn't make syntax highlighting for. So let me know if you're good to go. Okay, great. So have a good week, everybody. Please get in touch if you need or want any assistance with the project. If we are beyond my schedule for Zoom, but you want to do a Zoom, just please send me a Canvas message and request one, and we'll schedule one and do a Zoom. Otherwise, have a good week, have a good day, and I will see you on Monday for our last meeting next week. I probably will not have finished grading the projects by then, but I'm going to get up super early on Monday, and I will try. So we'll see where we're at, but one more meeting. So thanks for being here. Have a good week. See you later.